And so in zone B, we did see the cracking. We saw the flow slide starting to go, but we saw the arrestment. And here we have a profile AA prime. And so you can see how relatively gentle this slope is that we're looking at. If we zoom in here, these drone images really allow us to get into the details. And nowadays, frankly, they've even gotten much better with the types of processing that we can do. What you also will note here is right at the boundary of the north side of the flow slide, we have a housing complex, and that housing complex got ripped right in half. And so that also gave us, in addition to obviously these DEMs, it also gave us a measurement of how much this flow slide displaced before it was arrested. And based on these measurements, it was about 80 meters of displacement downslope before the flow slide arrested. We can also look at the bird's eye just from satellite imagery, and we can draw on the footprint of the flow slide. So in this case, you get a really nice view of that housing complex that was ripped apart. What's interesting, obviously, the housing on the boundary of the flow slide got very damaged from this movement, but on the flow slide, the houses or the housing that was further away from the boundary just more or less went along for the ride, rafted down, and then obviously off the flow slide, those houses did not experience so much damage. So we ask ourselves, right, why was Lolu Village arrested? Why didn't this turn into the same significant flow slide like Potobo or like Jonah Oge? And we don't have a definitive answer for that. We speculate, though, that it has something to do with the subsurface and it has something to do here with the water table being perhaps lower than it was at other parts in the East Palu Valley. There's other speculations about soil types in this area, but those are unanswered because we weren't able to get in situ data. Here's some photos at Lolu Village. So the top left, we are standing essentially at the crest. Well, no, sorry, we're standing at the main road there, sort of in the middle, but right at the boundary of zone A and zone B. And we're looking down slope. And so we can see these significant tension cracks that are forming. And then the picture in the top right is if we turned directly around. And so we can see this telltale sign of these tension cracks, and that continues here upslope another couple hundred meters until we reach the irrigation canal. We were able to talk to the residents of this house that we see in green here to understand the observations that we were making. And they described the shaking, and which was important because we didn't have many seismometers in this location. So we were relying on the population to be seismometers for us. And they described the shaking as a brief horizontal movement, followed by a short quiescent period, followed by a sharp vertical drop. And so all indications are that in this area, the earthquake motion was relatively short in duration, but very high in intensity. And that would check out with what we know about the rupture directivity and the direction of the rupture and the super shear type of rupture that we saw. We show in the bottom left, we show the ripped apart housing complex, and we can see, and these are the houses that got rafted. And so again, the houses are damaged, but they were not a life safety issue in this case. They rafted down, and the residents were able to make their way out. And on the bottom right, we see the accretionary wedge, or the deposition of that flow slide. So if we switch gears here and we look at Potobo, we have a very different situation. This is the case of a flow slide that went, and it really unleashed its full physical power and potential. And so in this case, right, zone B, we have demarcated here, walking around, lots of disintegrated soil blocks from soil A, lots of evidence of soil liquefaction. Zone A, I'll show some pictures, but we have, at the very boundary there, we have more disintegrated soil blocks. As you move up, or I should say, as you move east towards that irrigation canal, you get more and more intact soil blocks that are back rotated. And then in zone C, we see the accretionary wedge. So this is what it looks like from the satellite imagery. We had a couple of eyewitness observers standing near where you see the sluice gates. And what they described unanimously is that this failure started down at the bottom, in this picture, the bottom right, which would be the southeast corner. Okay, and so they saw this movement starting first. And so we see that lobe of zone C, the small lobe. And so this is really a compound flow slide. And after that flow slide had gotten going for a couple of minutes, the entire thing ripped apart. And then we started seeing movement, or the eyewitnesses started seeing movement here in the northeast portion of the flow slide. And that's when things really opened up, and we see this very much larger lobe here in the northern portion of this flow slide. And so this is very close to the Palu airport. And unfortunately, this area of Potobo, because it was closer to the city of Palu, was more populated. And so unfortunately, more people lost their lives or were significantly injured in this particular flow slide. So here's what I was talking about. So top left, these are the back rotated soil blocks that we see near the headscarp, near the irrigation canal. If you more or less now look at to your left, you're going to be looking out on zone B. So these are completely disintegrated soil blocks with a bunch of sand boils showing evidence of liquefaction as we look downslope. The picture in the bottom left is right at that boundary of the smaller lobe. And so we see, the houses obviously right on the boundary sustained significant damage, but it didn't take very far off that until the houses were more or less undamaged, other than some architectural issues. And then the bottom right is showing the accretionary wedge. It's hard to see the scale in this picture, because this flow slide was so large. Okay. So we are able to do some CPT at the Potobo site. These are not directly on the flow slide. We felt like it was disrespectful of us to do that. And so these are located just north, but outside of the flow slide boundary where there was no damage. Now, what we can see based on the soil behavior type from Robertson is that the upper few meters of soil up to the upper 3 or 4 are characterized by these deposits of clean to silty sand. And those are precisely the types of deposits that we would expect to liquefy. And it's also no real surprise based on the depositional environment at this location, being at the base of alluvial fans, and in a very high precipitation environment, and also being sort of at the edge of that alluvial plain caused by the flooding of the Palu River. So based on the CPT, we performed some simple flak analyses using more or less more Coulomb parameters. And what we wanted to see is if we could model what we observed in the field. And so we did that, and we were able to model these flow slides, even as gently sloping as they are. And our model here, in this case, is for if you look at the bottom figure, the shear strain figure, we're looking at a water table, in this case, of 1 meter below the surface. And we're looking at this residual shear strength at the end of liquefaction, or sorry, I should say at the end of earthquake shaking, when the soil is still in a liquefied state. We're looking at that as a ratio of 0.04, which is what all of our empirical guidance, it would kind of predict that this SU over sigma V prime would be on the order of 0.03 to 0.05 range. So we were able, just with this simple model, to replicate what we would expect to see in the field and replicate these flow slides. So we looked a little bit further at a sensitivity analysis here. And so we ran this FLAC model with different residual shear strength ratios, SU over sigma V prime. And we also looked at different depths to the water table, starting at the worst case water at the surface and then moving down. And what we can see, well, what I should say is at Patobo, talking to eyewitnesses, talking to farmers there, they were telling us pre-earthquake that their wells were about 1 meter below the ground surface. Okay, and so if we look here at a shear strength ratio around 0.04, and we look at the 1 meter below, we would expect our unstable region to be about 400 meters. And this really corresponds very well with the mapping of zone B that we did at these flow slides. Notably, at Patobo, after the earthquake, those same farmers noted that their wells dropped over the course of a few days or even a few weeks, and they stabilized around 10 meters under the ground surface. So our modeling here suggests, right, if we had had those deeper groundwater tables, that we would not have expected these flow slides to occur. And so, for at least for this earthquake, the Indonesian earthquake, this kind of brings us maybe to this lesson learned, and that is that land use matters greatly when we're discussing the effects of these earthquakes. In Patobo, at Lolu, at Jono Oge, the agriculture was mostly rice farming. And so the farmers there had to keep the water table relatively high. And the government installed an unlined irrigation canal running along that side of the valley in order to help those farmers. It was really for two purposes. It was a flood control device based on just intense tropical rains that are occurring in those East Valley hills, but it was also to help the rice farmers keep their water table elevated at the times of the years that they needed to. And so this land use was prevalent. Also, the Palu was creeping further south, obviously, as population grew. Patobo was marketed as a place where you could drill your well and you didn't have to drill it very far down until you hit water. And so It was actually a wealthier suburb of Palu for that reason. And so the land use here really, really mattered because of the elevated groundwater table, because of the land use. We suspect that liquefaction occurred a lot more spectacularly than it would have at this elevation otherwise. And because of that, we got these massive flow slides that unfortunately caused a lot of damage. I get asked questions like, what do we do about this? And the answer's not obvious to me. Obviously, farmers have to make a living. They have to feed the people in their city nearby. And so I don't know how you control land use. Now, there's some things you could do with the canal in terms of lining it, making sure you're not getting excessive seepage there, and design of the canal to handle rainstorms more effectively. So there's some things that you could do there. I think from a geotechnical earthquake engineering perspective, maybe what's interesting here is thinking about looking at satellite images like the one we're seeing here and trying to spot problematic areas before earthquake occurs or earthquakes occur. But even if we did that, right, in terms of liquefaction here, we would maybe say, okay, around the Palu River, we expect liquefaction. That makes sense. Okay, so buildings built near here, probably going to be on alluvial deposits. Let's think about that. But without knowing the land use a priori, we probably would not have predicted these flow slides because of how gentle the slopes are. So if we're going to move ahead in the field about using these satellite images, predicting things like ground failure, uh, caused by earthquake shaking or liquefaction caused by earthquake shaking, we have to overlay these land uses on top of those maps. Okay, so let's shift gears a little bit, and I'll go to part two, and this is my work in Turkey following the 2023 earthquake there. This was funded by NSF Rapid, and we also got support from the USGS, from USAID, and we got some support from Caltech as well to complete this work. And we have this publication out in the Seismological Research Letters if you're interested in this work. So here's the context in Turkey. And so we are in the south central part, and we're primarily on the East Anatolian fault. And so in February of 2023, the main shock occurred, a magnitude 7.8. It occurred on a tributary fault to the East Anatolian fault, the Narla fault, and then it bilaterally ruptured that East Anatolian fault, and a left lateral strike slip since. Not very long later, same day, a magnitude 7.7 occurred north of the first epicenter on the Chardak fault, another fault associated with this East Anatolian fault zone. And so that's what we see here. And we see the regional context in the map to the bottom left. Obviously, the USGS pager estimated a lot of damage caused by this earthquake, and primarily because it was near population centers and the earthquakes were relatively large. So if we look at this context, Turkey is actually very size or tectonically complex. It's located in the zone between, or the Anatolian fault here. It's located between the zone of the Eurasian plate and the African plate, and then this Arabian plate. So we have subduction here, we have transcurrent faults, and we generally, Turkey is getting squeezed here to the west, and we're getting this sense of movement on the order of 10 millimeters per year. And so what this does in effect is it creates these two transcurrent boundaries. The North Anatolian Fault, which has been well studied because it runs through some of the major population centers up north. And so, the 1999 Esmet and Duce earthquakes occurred on that fault zone. And then it creates this East Anatolian fault zone, which has also been seismically active for a long, long time. So in the bottom figure, we see some of the important earthquakes that have occurred over the last couple hundred years and their rough magnitudes. We also, this area, we are in Mesopotamia. And so we have also a rich oral history in this location of earthquakes occurring going back centuries. So in this case, we really sat down before we went and we came up with a research motivation. Why are we going? What are we trying to accomplish? So what we realized that this was a very large surface fault rupture. The 7.8 event ruptured nearly 345 kilometers on the surface. And then we had the aftershock on the Chardak fault that ruptured another 175 kilometers. So from a understanding surface fault rupture perspective, this earthquake is critical. It's nearly pure left lateral strike slip motion. And so, at least from an engineering standpoint, this would have similarities with other global faults, like the San Andreas fault here in the States. Now, I do point out this is from an earthquake engineering perspective. I think when I talk to people who are actually structural geologists into tectonics, they shudder a little bit at that bullet point. And there's critical perishable data for forwarding these fault displacement models, and as a consequence, our probabilistic fault displacement hazard analyses that are critical for engineering analyses. So we had some research questions, and I'll call these initial. On my side of the aisle, the earthquake engineers, we are just curious about what data we can actually collect once we get there, what is still available to us. Can we then use those data to improve our fault displacement models? And then what is the uncertainty, or how does the uncertainty propagate throughout these models? Our earthquake geologist colleagues who went with us had another list of questions that you can see there in the right circle. And then we both had an interesting question, which is self-similarity valid? And what I mean by this is, can we take information we use from lower magnitude events that occur more frequently, and can we scale that type of guidance or those types of observations up to these magnitude 7.8 or larger? Okay, so some equations here. We have the probabilistic seismic hazard analysis. Most of you have seen this hazard integral. At the heart of this hazard integral is this conditional probability, and that conditional probability is foundationally computed based on ground motion prediction equations. So these modern ground motion prediction equations, right, we have some ground motion intensity measure y, and that's going to be a function of magnitude, distance, style of faulting. If you're on a hanging wall, your site velocity, how deep your sedimentary basin is, so on and so forth, as well as some standard deviation, some uncertainty factor. Well, our fault displacement models are at a point now where probably our ground motion prediction models were in the late 60s, early 70s, where we really are up to the point where we're looking at predicting fault displacements based on magnitude, distance along the fault, and a style of faulting, and that's about it. And we have a pretty large standard deviation. And so after we got into the field, we started coming up with these additional research questions that we aim to continue to study and answer. What's the best aleatory variability model for your fault displacement? Is it log normal like ground motions? What's the best modeling philosophy that we can use? Should we think more about a physics-based modeling, or should we focus most of our energy on these empirical-based models, or can we somehow do a combination of the two? What are the next modeling terms necessary? Is it the shear wave velocity? Is it the depth of bedrock? What's going to make, at least in the near term, these very empirically driven fault displacement models better? And maybe most importantly, can we even make displacement predictions that are useful for engineering purposes? So before we went to the field, we did our due diligence with remote sensing. These are satellite-based images that my colleague Nadine Reitman worked on at the USGS, and she was able to take at least initial estimates of what these fault displacements were along the strike. And after she did that, and after we talked to our Turkish colleagues who participated in the reconnaissance, we came up with this study area. And we were interested in this intersection between the Narla fault, the subsidiary fault where the main shock actually initiated, and the intersection of the East Anatolian fault, which bilaterally ruptured afterwards. And so from that, we developed our fieldwork goals, which were to map these areas that had not been mapped by previous earthquake geologists, to record the perishable surface displacement data, and to evaluate this collected data from the earthquake engineering perspective. Can we make these fault displacement models better? So here's some of the work that we did. On the left, you see my colleague Greg Labrantiadis taking some GPS points. That's an onion field. And so if you look further afield in the photo, you see my two other USGS colleagues right at the fault scarp, and you can see the onion field has moved left laterally on the other side of that fault scarp. On the right, we're doing the same thing here, but we're looking at a forest road, and we're looking at the structure that we're seeing here is the edge of the road. And so we're using the edge of the road here to map the fault displacement at this particular piercing point. So we use these styles of technology. Primarily, we used a lot of tape measures at piercing points that were not very high quality to estimate the fault displacement at those locations. We used the GPS device at higher quality piercing points. And then we also used handheld remote LiDAR to help us map some of these more interesting cases of fault rupture. Now, what would have been nice is if we would have been able to fly the structure for motion drones like we did in Indonesia. However, we were not allowed to do that. We were not able to get the permits required. Turkey has a bit of a stronger standard, especially with respect to any flights near military installations. So we were not able to get permission to do this and make these flights. Doing so would have been incredible. We would have been able to take the satellite data that Nadine used for the initial estimates, and then we have been able to create these high resolution DEM models to really highlight piercing points that we could have gone to on foot and spent more time at studying. Okay, so at the end, here's what we did. We surveyed this part of the intersection zone. We came up with these displacements here given in meters, and we were able to fill in a missing zone of fault displacement along this fault at this intersection zone that other earthquake geologists hadn't gotten to yet. And so you can see our data maybe more aptly in the bottom left. A complete measurement means that we think we got the complete displacement field around the fault. An incomplete measurement means we don't think we went far enough perpendicular to the fault strike to measure all of the displacement that we could have observed. And that's largely just due to physical boundaries or being on the sides of mountains, things like this. Okay. So, what are we thinking in terms of fault displacement model improvements? I think from an earthquake engineering standpoint, this is probably where we stand to make the most strides from the observations of this earthquake. And the things that we were interested in were, again, the self-similarity or the magnitude scaling. These earthquakes were relatively large based on a lot of the earthquakes that we had used in the past to calibrate our fault displacement models. Obviously, making current model comparisons versus the field data we collected, comparing our data to the data collected by others, either before we went or after we got back, thinking about the importance of near surface geology and soil conditions, and then finally estimating the uncertainty of displacement measurements in the field. Now, the other thing I'll note is that we need more data in areas where we expected surface fault rupture, but we did not see it. So the so-called null hypothesis, and this is the same for other ground failure in the geotechnical earthquake engineering space. We really need to go out and understand why ground failure didn't occur at locations that we expected it to. Here's all of the data in the database for fault displacement models. And so you can see these Turquia events were the 4th and 11th largest events respectively. And so this is why these events were critical for us to understand the magnitude scaling or the self-similarity. Obviously, we would like for that to hold as much as possible because we're going to get a lot more of these smaller events. So some observations here, though, is that we do see a behavioral threshold at magnitude 7.5. Self-similarity does not hold from these limited observations that we have. Keep in mind, right, we only have 10 other observations above a magnitude 7.5. So we don't actually know if this is a correct observation or if it's just a data limited observation. But what we're seeing is kind of a break in behavior, and we're getting lower fault displacement estimates than we would by just kind of, if you will, linearly and log space extrapolating our model above a magnitude 7.5. So we need to change our fault displacement models to incorporate this threshold, or we need to understand this threshold better and whether it makes physical sense. Okay? I think what it really shows here is that magnitude is not the only earthquake-related proxy for fault displacement. Here are data plotted. These are data collected by our Turkish colleagues, and here are two fault displacement models. And solid is a model by Mark Peterson and many other colleagues from 2011. It's kind of the standard for strike slip events. And dashed is a model by Labyrinthiadis and Abrahamson, came out last year in Earthquake Spectra. And so what you see here, obviously, is you see significant scatter. Maybe in an average sense, these models are doing fairly well across the length or the strike of the fault. But we're also seeing outliers, right? We're seeing maybe the normalized fault length of 0.6 and 0.9. We're seeing much higher fault displacements. So why are those observed there in these particular scenarios, what could we possibly do to improve these fault displacement models, or can we? Here's our data and plotted very specifically at our area along the East Anatolian Fault. And it's got some other data. And so in general, we're seeing fault displacements on the order of about 4 meters across this length of the fault, or the strike of this region of the fault, though we do see here a zone of higher displacements on the order of 6 meters. And most of what you can see here, comparing our data to others, is it really lines up pretty well. Okay. Now, we'll also notice for engineering purposes, this is significant scatter. And then furthermore, we haven't really examined this further, as our models do less well fitting the magnitude 7.5 aftershock. Okay, and so some other notes here based on our study site. Our study site is relatively small compared to the entire fault. We decided to do a deep dive. We decided to do a mile deep and a foot wide rather than the opposite. And so obviously, if we had more time, more budget, so on and so forth, we would have done more of these things, or if we could have gotten permitting. So maybe those are things that some of the things could be done, like fault trenching in the future, and some of our colleagues are already doing that work. We also went back this past year. We carried a bunch of surface wave testing apparatus with us. And we did a bunch of surface wave testing to try to get values of shear wave velocities in the near surface. So we have some sense, and this is a finite fault solution from my colleague, Dara Goldberg at the USGS. We have some sense here that the surface displacements must be higher at locations where we have more slip on the fault itself. But it gets complicated as you get to the near surface soils and geology. And so we know that that's something that we need to incorporate as we make these models better. And finally here, we looked at structures at these piercing points. I'm back here on the road I showed earlier. We're mapping the left side of the road, but there's still a lot of uncertainty about where exactly you're mapping that structure, as well as uncertainty in the GPS device itself and that measurement. So here we're able to do about 1 million different analyses. So we did a Monte Carlo, and we considered the uncertainty both in our measurement as well as the GPS measurement. And so with that, we're able to come up with these distributions of displacements to where we can get more formal standard deviations. Now in the field, earthquake geologists have traditionally done this by eye based on scientific judgment. And it turns out that they're really, really good at this. So our more quantitative approach here that we're showing gets about the same standard deviation that the earthquake geologists just specify based on the eyeball norm. Okay. So if I'm thinking about the lessons from this particular event, and we're looking at this overview map, the things that we really need better fault displacement models, because obviously things like pipelines, civil infrastructure, they're going to cross faults, and we know that, and it's impossible to avoid. But what's really tough here is we are handcuffed by the limited data that we have from previous events, as well as how tough it is to get some of this data reasonably and well enough and understand the uncertainties, and then to be able to come up with these simple fault displacement models that are simple enough to use in an engineering sense, but complicated enough that we actually have the confidence that we could do something like design a pipeline with them. So I think there's a lot of work to be done in this area. Ideally, we would have more observations, but we don't. And we can't really just wait around for the next 10,000 years for a bunch more earthquakes to get better at this. So I think probably in this field, we're going to have to do some numerical modeling. We're going to have to do some numerical experiments. We're going to have to do some physical experiments at larger scale laboratory facilities worldwide to try to develop better fault displacement models and just modeling techniques and gain that confidence. Okay, so last two slides. These are more about earthquake reconnaissance in general. One thing that after I've done 6 of these post-earthquake recon trips now and led a couple of them, I'd say always develop scientific questions that you want to answer before performing any recon activities. And if you can't develop scientific questions that are interesting, you probably should not go on that trip. And what the scientific questions do is they focus the team members that you would need, the expertise that you would need in the field. We knew in Turkey, for instance, that we needed a significant earthquake geology component. It'll focus the equipment that you need, right? We knew up front that we could not bring the drones with us, so we left those at home. It will focus the schedule. How long do you need to be there to get the information that you need? Second, I like this old adage from the US Army, plans are useless, but planning is invaluable. It's a little bit tongue in cheek. Obviously, plans are useful, but the the planning process itself is where you really learn and develop these scientific questions. And so during this, we use government agency information like the USGS, social media, and we use the satellite, the remote sensing information to really guide our scientific questions and to guide our reconnaissance planning. And then finally, obviously never get in the way of emergency operations. This sounds intuitive, but I've seen this more times than once. Always respect the visa and host processes, no matter if they delay your start in the field. And this kind of follows hand in hand with starting early, work with the local scientist, and then continue to work with them. They open up a massive number of doors for you to perform good science and to learn from the disasters so that hopefully they will never occur in the same way again, or that we can at least engineer and protect people. And then do not count on all the technology being available in the field. Obviously, we were not able to use drones, though that would have made our reconnaissance effort so much better. And then finally, this goes for folks who are advising junior engineers or postdocs or graduate students. This work is not for everyone. We've had students who have had to leave this type of work because of the emotional toll that it can take on you. So it's not for everyone, and that is okay. But for myself, given the fact that we have this destruction that occurs, I want to go out. I want to learn what we can from it. I want to pass the information on. And I hope engineers and scientists, like the folks on this call, can come up with better procedures and keep us all safer against future events. Thank you very much.
Great, thank you, Ben, for the excellent presentation. So, yeah, now we welcome the question. So I encourage you put your question in the chat box. We still have time. Ben did a good job and time control. Okay, so let me go through one by one. So the first question we have is how we can define seismic, how to map magnitude minimum and maximum?
Yeah, that's a really that's a question that we could easily spend another 50 minutes talking about. And I think there's some parts of the world that we just have a lot better recordings, a lot stronger recording history that maybe, and we also have some tectonics and geological studies in those areas so that we could feel more confident saying, hey, this is the range of ruptures that we expect to see. We only expect this fault segment to rupture, or we expect that fault segment to rupture, so on and so forth. But I think in most parts of the world, this is still very hard to define reliably, um, just based on the lack of recordings that we have. Uh, if you look at the building codes, obviously this is a question that comes up a lot. And so they're going to have some guidance for given regions for how you might do this, with a grain of salt, so to speak.
Okay. So next question, you presented a plot of length versus residual strength for different groundwater depths earlier in the presentation. Can you please expand on it?
Yeah, I don't know in what direction you would like me to expand on it, though. Do you want more details of the model, or should you want to look at the plot again and think about it?
So who is the, okay, I believe,
Antone.
yeah, Anton, if you can speak up if you want, or you can type down.
Can you hear me?
Yeah.
Yes.
Okay, that's great. No, I guess we can bring it back, and it sounded to me like I would have expected the opposite trend, but I don't know. I may have thought that the black line should be in the other, just before the purple line and the opposite way, but I may have been wrong. But yeah.
Let's see. Yeah. Um, yeah, so for lower values of this residual shear strength, we would expect basically the entire region to be unstable, especially for these higher groundwater tables that we see up here. And then as you get more residual shear strength, and again, we kind of think we're somewhere between 0.03 to 0.05, just based on the cone penetration testing and some information from our Indonesian colleagues. Um, and so essentially what the black line showing going out this far is if we use a higher value of this residual shear strength, we still expect flow sliding. So that's intuitive to my physical understanding.
Yeah, that makes sense. Thanks, man. Yeah.
Oh, sure. Thank you.
Okay, good. So let's move to next question. I mentioned that at the point 0.9 normalized four lengths, the proposed displacement model 2011, 2024 have less displacement value than the most observation point. Can you explain this?
Okay, let's see. Have less dis. Oh, yeah. And so there's several points, or sorry, several regions along the strike of this East Anatolian fault. And towards that region, that is point 0.9, the fault actually ruptures through pretty competent mountains. And so without having, like, even drones would be tough, but without having closer up aerial lidar or something like this, it was impossible for us to go in on foot and map these locations. There's a couple other locations along the strike of this fault or regions. One is an ancient lake bed. And so the fault displacement there got widely distributed, and it was not obvious from the ground surface, where the surface expression of the fault rupture was. So that's those holes that you see along the strike of the fault are generally either mountains that we can't traverse or things like swamps or lake beds where the displacement gets distributed, and it's too confusing.
Okay, so the next one actually is another question. Just so
Thanks, Yolanda. You too.
okay. So the next one is pretty long. I will read out. It's can include several questions. Thanks, Ben, for the excellent presentation. I'm curious, when mobilizing to active seismic regions, is your team concerned about a possible recurrent event during the field work, especially given the travel and access challenge? So maybe just let's first and then move to next. Let's kind of three questions more.
Yeah, that's an exceptional question. After the Indonesian earthquake, we did not go until mid-September. And so we were there about 7 weeks after that earthquake occurred. And so we did feel small aftershocks, but usually by that point, the major aftershocks are going to be um, quelled. And so, at least in all of my time, I've never experienced anything very significant. And Turkey, because of getting permits and permissions and what we needed to do, as well as securing the funding, right? We went in May and June of that year after February. So we were there months after. And again, we did actually feel some very light rumblings, but we were there far enough to not really be that concerned about major aftershocks. But what I will say is it has a major psychological effect on the actual residents who had to experience it. And so maybe the thing that's important is during these eyewitness interviews that we conducted, we had to be very sensitive because we were talking to folks who are still suffering from PTSD based on what they experienced, what they had seen. And even us, right? I still have images burned into my mind here that I can't get over. And I didn't have to experience um, these earthquakes firsthand. I think that's what's important there.
Okay, so next one is how closely do preliminary satellite-based estimate of a seismic event match the field data your team collect later?
Excellent question. Yeah, really depends on the region of the world you're in and the available satellite data. Because I was working with my colleagues at the USGS and Nadine, who's an expert on this topic, she was able to get access to pretty high quality, recently flown, high resolution data. And because of that, the estimates she was able to make were very good compared to what we saw in the field. Um, and other events in the past, like when we were trying to do this in Indonesia, it was a lot harder, and we had to focus on that small region, and we had to do a lot of this work um, by hand, or the graduate student at Auburn had to get our change detection. So that has really increased um, our understanding of post earthquake of just the change in technology, even over this last 7 years or so, has been incredible for helping our understanding. And then I think you said, yeah, so I think that the impact is usually pretty major for us.
So that will be the last one, right? So that's the timing of post event data. Yeah. Okay.
Yeah.
All right. Good. So the last question, we kind of 1 minute is over. Let's get how you observe that the cell similarity occur below magnitude 7.5. Can you put some insight on that too?
Yeah, it's just simply plotting the fault displacement data that we have available, and we normalize it by the normalized length along the strike of the fault. That has some problems itself because faults aren't straight lines, as we saw in all of my maps. So that's like one thing to keep in mind. But if you do that and you control for the distance along strike in that rudimentary measure, and then you look at the average displacement in regions along strike as a function of magnitude, then you can plot these lines, or you can plot how the displacement changes. I don't have one of these plots in my slide appendix, otherwise I would show you. But then you can do the fitting, and you can, what we see here is that for lower magnitudes, obviously there's some magnitude below which we're not going to get fault rupture because it's just too weak. But for those smaller magnitudes, so to speak, but are still able to cause fault rupture, we kind of see a linear trend in what I'm talking about until we get up to somewhere in the zone of, let's call it 7.5. That's fuzzy also, obviously. And then above that, we kind of see that they don't continue to follow that linear trend. They become less than we would expect. So we have this piecewise function. Now, what we don't know, because we don't have many constraints from above, is we don't know if this is a real observation or if it's just a lack of data in our inventory. And so I think this is where maybe these numerical experiments and physical experiments could shed some light.
Okay, that's the end of question list. So we run 4 minutes over, and so we over very good. Thank you, Ben and Kasha, for the excellent presentation, and thank you all for participating in this workshop. I'll see you next week. Okay, thank you, guys.
Thank you. Bye-bye.